Hello guys, welcome to Physics Grad. In this video, we are going to study about some of the important properties of the Lagrangian function which we encountered in our previous lecture. So in the previous lecture, we studied about the principle of least action, which basically says that the correct path followed by the particle corresponds to the one where the action denoted by S is minimized. And for this minimization to happen, some conditions must be followed, which are nothing but our Euler-Lagrange equations. Okay. Now the important question is, why did we say that the Lagrangian depends on the generalized coordinate, the generalized velocity and time? Why not depend on, let's say, q double dot, which is the generalized acceleration, or higher derivatives? So the question is, why not L be dependent on q double dot, q triple dot, and so on, or any other variable other than the three that we have considered here? What's so special about L being dependent only on the generalized coordinates, the generalized velocity and time? So how do we answer this question? Now, to answer this question, we have to consider some examples. So what is our main goal here? So our main goal is to basically completely characterize motion of a particle or some set of particles. For simplicity, now we are going to just consider one particle. So what do we mean by this? How do we say that the motion of a particle is characterized? So for this, let's consider a particle moving in one dimension. Okay, so in one dimension, a particle can only move along a particular line, and let's say x denotes the position of the particle. Now, what are the different things that we need to characterize the motion of a particle in one dimension? So what do we need? What do we need to characterize motion in 1D? So you would immediately say that obviously we need to know the position of the particle, we need to know the velocity, and acceleration, and so on. You may keep listing out many different variables. But the question is, do we really need so many different quantities to characterize the motion of a particle? Or can it be just characterized by knowing just few of these quantities? So let us try to answer that question. So first, let us consider the position of a particle. So in 1D, So let us say that it initially was at position x1 and finally it goes from position x1 to x2. Okay. Now, since we are only going to talk about one dimension, this is going to be our one-dimensional position axis. Then the particle, let's say that it has traveled from x1 to x2, okay, via some points which fall in this line. So what information is this particular diagram give us? Okay, so what does this tell us? What does this diagram tell us? Or what information is it given? So all that it is saying is that it tells us where the particle has been, or in other words, it just says what are the different coordinates that the particle has visited, okay, but it does not say the order in which the particle visited each coordinate. So it doesn't tell us whether, let me take a different color, whether the particle went from here to here, then to here, then to here, then here, then back here, then here, and then here. So this is one of the possibilities. Or it could have started over here, gone 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 here, and finally ended up here. Or it could have gone in a completely different way. So it could have gone very close and then come back here, then come back here, then come back here, then come back here, 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 and finally end up here. We don't know. So we do not know the order in which the particle visited, the order in which the particle visited each of the coordinates. So this particular diagram does not give us that information. Okay. Also, it does not say how quickly the particle changes its coordinate. Okay, so it doesn't say how fast it moved from here to here, or how long it took the particle to go from this particular coordinate to this particular coordinate. So this diagram does not give us that information. So therefore, since we don't know these, this implies we can't characterize the particle's motion with just position information. Okay, why? Because we do not know these things. To characterize completely the motion of the particle, we need to know these things, and this information is not provided by just knowing the position of the particle. And I want to emphasize here that this diagram is not telling us the position of the particle with respect to any time scale. I have not talked about time whatsoever in this particular diagram, which gives us just the position information. Okay, so what is our conclusion? Our conclusion is that just knowing the position is not enough to characterize the motion of a particle. So let's consider now just velocity. Okay, so what will happen if we just know the velocity? So now we just know velocity information. Okay, so from this, what do we know? What information do we get? All we know is that what are the different speed with which the particle was moving. So it just says what are, in this case that is in one dimension, what are the different speeds with which the particle was moving. Okay, so if I had to represent this diagrammatically as before, how would I represent it? Okay, so it may be the case that the particle was moving from the initial point x1 to x2 with the same velocity, in which case, so for example, if the particle was moving with constant velocity implies the diagrammatic representation will be just a single point given by v. Okay, so that is all the velocity information tells us. What are the different speeds with which the particle was moving? Or we can consider another example where the particle's velocity takes only two possible values. Okay, so you can consider a particle moving back and forth with the same similar speed. So two velocity, so the diagram will become simply 2 points. So that will be v1 and v2. Or it can also take some range of velocities. So this can become, and it need not be, continuous range. So it can just be some range of velocities from v1 to v2 and some other range v2 to or some v3 to v4 and so on. It need not even be continuous. It can even be, some discrete set of points we do not know. Okay, so that is what we can imply by just knowing the velocity information. Okay, so that is what we know. What do we don't know? So by just knowing the velocity information, we will not be able to imply what are the different coordinates that the particle has visited. So we don't know position of the particle. Okay, and once again, we do not know if the particle takes multiple velocity values. We do not know the order with which the particle takes the different velocities. So this is same as not knowing what is the dependence of velocity with respect to time. Okay, so In the same case as before, since we do not know these both, since we don't know these, this implies we cannot characterize. We cannot characterize the motion of the particle by just knowing the velocity of the particle alone, or by just knowing the position of the particle alone. And we can give similar arguments for the other quantities, like by just knowing the acceleration, whether we will be able to characterize the motion or not. Okay, so what do we need to know to completely characterize the motion? So that's the question we are trying to answer. So let us consider that, so let's say we know both position as well as the velocity. Then what is the case? So this means that so this implies we know at every position how fast the particle is moving. And since v is nothing but dx by dt, this is same as saying we know the slope of the x of t curve at every instant of time. Okay, so this is same as saying that we basically know x of t curve. So if we know the position as well as the velocity of the particle at every instant, or so for a given position we know the velocity, which means in principle at every position, because of this definition, we know the slope of the xt curve. So this is same as saying that we know the xt curve. And once we know the xt curve, so xt, this is the familiar distance time graph. Once we know how this curve looks, we can calculate the vt curve by just calculating the slope at every point in the xt curve. So in this case it will look something like positive, 0, negative, and then again positive, and so on, something like this. Okay, and from this we can in turn get the at curve by just differentiating this curve at every point, and that will lead to some curve like this, something like that, and so on. So by just knowing, so therefore by just knowing xt curve, we can know vt curve, at curve, and so on. So now we know exactly what is the order in which the particle visits the different coordinates and how quickly the particle changes its coordinates. We also know the position of the particle at every instant, and also the order with which the particle takes the different velocities, which is nothing but the vt curve. So basically we know everything about how the particle is moving, and therefore we can conclude that it is sufficient to know x of t, which in turn implies knowing the position and velocity with respect to time. So it is sufficient to know x of t or x and v with respect to time t in order to completely characterize the motion of a particle or a system of particles. Okay, so what is the conclusion? The conclusion is that it is enough to know the position and the velocities with respect to time, of course, in order to completely characterize the motion of a particle. Or in general, it's sufficient to just know relation between the generalized coordinate and the generalized velocities. So if we know this implies we know q of t, we know q dot of t, we know q double dot of t, and so on. So therefore it is enough if we know the position and the generalized velocities at every instant of time for the given particle in order to completely characterize the particle's motion. And that is exactly the reason why the Lagrangian is dependent on these three variables alone. I hope that this is clear. So that is why the Lagrangian depends only on the generalized coordinate and the generalized velocities and time. So therefore it's sufficient to describe a system with a function which depends on the generalized coordinates, the generalized velocity and time, and we call that function as the Lagrangian. And the Euler-Lagrange equations which we saw in the previous lecture, which basically says the following: d by dt of dou L by dou Qi dot minus dou L by dou Qi equal to 0 for I equals 1 to 2 till s, where s is basically the number of degrees of freedom. Okay, so this Euler-Lagrange equation basically gives the relationship between q dot and q double dot. Okay, so this q double dot information we get from this part of the equation, and since L depends on q dot and t, this particular equation is going to give us the relationship between q dot and q double dot. So for example, if let's say the L is dependent on some aq plus bq dot square or something like this. It can be anything, any function of q dot and t, let's say plus t, something like this. Then let's say how does this equation turn out? So that will become d by dt of dou L by dou qi dot will be 2bq dot minus dou L by dou qi, so dou L by dou q, so that will be a. This is equal to 0. This implies 2b d by dt of q dot is nothing but q double dot minus a equal to 0, or q double dot is equal to a by 2b. So this is the case which, if we recognize, of motion with constant acceleration. Okay, so similarly we can have any functional form of the Lagrangian which depends on the generalized coordinate, generalized velocity and time, and the Euler-Lagrange equation will give us some relationship between q dot and q double dot by simply applying these conditions. Okay, now if you notice one more important thing, so the Euler-Lagrange equations, these are basically S second order differential equations. Okay, and since they are of second order, each of the equations, when you find the solution, will contain two arbitrary constants, which implies in total we will have, so the solution involves 2s arbitrary constants. Okay, so this in turn implies we need 2s minimum, so we need a minimum of 2s initial or boundary conditions to get the solutions for the Euler-Lagrange equations. So these 2s initial conditions can be the initial set of generalized coordinates and the initial set of velocities, for example. So if you consider motion of the particle in 1D, then we will just be talking about the x coordinate, the x velocity and time. So here the value of s is 1. So when we solve the Euler-Lagrange equations, we will need two constants. We'll get two constants in the solutions, and to find these two constants we need two initial conditions, and these two initial conditions can be the initial position and the initial velocity, which is nothing but xi dot. So if we know this, and if we know the Lagrangian, we can find the equation of motion and find out what is the trajectory of the particle, or completely characterize the motion of the particle. So that's it for this video. To summarize what we talked about in this video, we basically said that the Lagrangian of a particle, or we said that it is sufficient to describe the system by a function which depends only on the generalized coordinate, the generalized velocity and time, and we need not worry about the dependence on higher derivatives, because if we know these three quantities, it means in principle we can completely characterize the particle's motion. And the Euler-Lagrange equations are a set of S number of second order differential equations which yield 2s arbitrary constants, which in turn implies that we need 2s initial conditions to completely solve how the particle moves. Alright, thank you for watching. See you next time.